Now we've determined that our original function f of ty was of this form. Our original equation from which we obtained everything was df equals 0, and that has solution f equals constant. We've recovered the function f. It's equal to this. So our final solution is given, at least implicitly, by t square root of y minus e to the t cosine y plus t squared over 2 equals c. And I've taken a little liberty with c. C's on this side. I've moved it over this side, but f is equal to constant, and that constant will absorb this constant, and there's no reason to call it anything but c. Now this is so for any constant c. We could, and often would, attempt to solve this equation for y, but seeing a square root of y here in one term and a cosine of y in another term indicates that we're not going to get a closed form solution for this equation. Now we could use software, or we could use graphing techniques to attempt to graph our solutions, and I don't even right now want to think about what the solutions to this equation would be, although with a little analysis I think we could make an attempt, but that's really beyond the scope of what I'm going to ask you to do in this course, so there'd really be no point in it. No point in putting it on video, and really not much point in me thinking too hard about that except to exercise my brain. So we see that we have a function of t and y equal to constant, and that is going to correspond to a locus of points in the xy plane, and there really aren't any restrictions on the domain of this function that are completely obvious, although they could well pop up in the process of solution. So we can do a y versus t, and we could do solution curves. They certainly don't look like this, but they might. For different constants, for different values of constant c, we'll get different curves.